All right, we're going to start with what seems like a pretty straightforward coding question. But trust me, this journey is going to spiral really fast into the mind-bending realities of non-Euclidean geometry and the deep, deep math it takes to stop our brains from completely melting inside a VR headset. Let's get into it.
So, this is it. This is the big question. And we're not talking about your average fantasy world with dragons and magic. No. We're talking about worlds where the very fabric of space is just different. Worlds where parallel lines actually drift apart, and the angles in a triangle don't add up to 180 degrees. I mean, where do you even start trying to code something like that?
You know, the first instinct for a lot of people is to ask, okay, what programming language do I need? But it turns out that's actually the wrong question. The language itself is kind of secondary. What really, really matters is the game engine, that foundational software that everything else is built on top of.
So if you're looking for that surface-level answer, here it is. For VR, you've basically got two main choices: C# with the Unity engine or C++ with Unreal. Unity's way more accessible, it's got a huge community, and it's actually what was used for a famous Hyperbolica game called Hyperbolica. Unreal, on the other hand, gives you that absolute peak graphical power, but you got to be ready for a much steeper learning curve. So yeah, the tools are there, but this is where the real story actually begins. Because look, picking an engine, that's the easy part. The real challenge smacks you in the face when you realize the world you want to build is fundamentally completely incompatible with the engine you're using. We're trying to fit a round peg into a square hole, but we're doing it on a geometric, reality-defining level.
And this right here, this is the absolute core of the conflict. Every modern game engine out there just assumes it's working in Euclidean space. You know, the flat, predictable geometry we all learned in school. But the worlds we're trying to build are hyperbolic, which means they're negatively curved. In a space like that, the shortest distance between 2 points isn't a straight line anymore. It's a curve. The engine's most basic assumptions are just wrong.
And when your basic assumptions are wrong, everything that's built on them just falls apart. It's a total cascade of technical failures. The engine's renderer, you have to completely throw it out and write your own. You can't just trace straight lines for light. You have to use a custom technique called ray marching to trace along curved paths. The depth buffer, the thing that tells the engine what's in front of what, it completely breaks. You'll have things far away popping in front of things that are close. And physics? Oh man, you got to rewrite the whole thing from scratch. Because an object you throw straight is actually going to follow the natural curve of space, a path we call a geodesic.
So fixing the code is one massive headache. But the biggest problem here isn't technical at all. It's biological. It's about what these impossible spaces do to the human brain inside that headset. And here's the bottom line. If you just throw a person into a non-Euclidean world without some very, very careful adjustments, they are going to get incredibly sick. And this isn't some minor annoyance. This is a complete show-stopping problem that makes these experiences basically unplayable for most people.
So why does that happen? Well, it's a fundamental sensory conflict. Your brain is getting into a fight with itself. Your eyes are seeing a world that expands and curves in ways that just defy everything your inner ear, your sense of balance, knows to be true. You move in what feels like a straight line, but suddenly the world appears to be rotating around you. Your brain, which has spent your entire life mastering how to get around in our nice, flat Euclidean world, just cannot make sense of the conflicting signals, and the result is overwhelming disorientation and, yeah, nausea.
But thankfully, there is a solution, and it's not some new piece of hardware or a clever programming trick. The solution is pure, elegant, and honestly, deeply mind-bending mathematics.
It's a concept called parallel transport. Okay, forget the fancy name for a second and just focus on what it does. As you're moving through this warped, curved space, parallel transport is constantly and minutely updating your sense of direction. It's making sure that your forward is always lined up perfectly with the curved path you're on, which gives your brain a stable, consistent frame of reference it can actually understand.
Think about it like this. In our normal, flat world, when you walk forward, your sense of forward, your direction vector, is constant. It doesn't change. Simple. But in a curved, hyperbolic world, if that vector stayed constant in the old-fashioned way, the world would literally seem to spin around you. Parallel transport is the process that continuously adjusts that vector, so your orientation feels stable, even while the space itself is warping like crazy.
This bizarre effect actually has a name. It's called holonomy, and it is exactly what parallel transport is designed to prevent. Without it, you could walk in a small circle, come back to the exact spot you started, and find yourself facing 90 degrees to the left.
It's the ultimate recipe for motion sickness, and this mathematical process is the only cure.
So what's powering this whole process? Something called Christoffel symbols. The best way to think of them is like the instruction manual for the curvature of the space. At every single point, these symbols tell the parallel transport algorithm exactly how to adjust your orientation to match the local geometry. They are the mathematical engine that makes these impossible worlds finally navigable.
Okay, so we have the problem, crippling motion sickness, and we have the elegant mathematical solution. So how does a developer actually put all of this together? What's the workflow for building one of these worlds?
Well, it pretty much boils down to a four-step process. First, you have to pick a mathematical model, like the famous Poincare disk, which is a way of mapping an infinite hyperbolic plane onto a finite circle. Second, you use that model's mathematical rules to define your in-game objects. Third, you translate the player's movement into the language of that hyperbolic model. This is where parallel transport does its heavy lifting. And finally, you use custom rendering shaders to translate everything back into the flat Euclidean space of your computer screen, correcting for all the bizarre perspective and depth problems along the way. And all of that brings us to one last really big thought. If our brains, which literally evolved to navigate a flat world, can be trained to understand and move through a curved one, well, what other fundamental rules of our reality are maybe more flexible than we think they are? It's a fascinating thing to chew on, and it all started with just a simple problem in code. Thanks for joining me.